In this video, we're going to take a look at the new cryptography problems labs on the Damn Vulnerable web application. I actually saw that they released the API lab, so I came to record that and then I realized that I'd missed this cryptography section. I swear it wasn't on purpose, even though I do hate crypto. Anyway, let's start off with the low security level. It says, this super secure system will allow you to exchange messages with your friends without anyone else being able to read them. Use the box below to encode and decode messages. So we've got an option to encode a message here, and we've got the option to decode. I guess the logical thing would be to just try to decode this message that it asks us to decode. And if we do that, we get a password, which we can just put in here and log in. So there we go. We've seen how we can decode this message. Let's see how the encoding actually works. I'll try and put in here, CryptoCat is the best, and we'll encode it. It looks a little bit like base64 encoding. You see the double equals at the end. Let's go to cybersecurity by the GCHQ, which has a lot of different tools for like decoding and decrypting and extracting things from images and everything. And we could try the base64 decode. We'll see that it doesn't actually produce anything very readable, so it doesn't look like it's just standard base64 encoding. We could also try the magic function, which is somewhere here, and that will actually try a lot of different encoding methods by default. Oh, it's changed the view of that. I'm not too sure why. It wasn't like that yesterday. But anyway, yeah, it'll try some different encoding methods and see if any of them produce some meaningful output. And it doesn't in this case. I'm going to get rid of that recipe. Let us do the base64 again. And this time we'll also try an XOR operation. So if you go down to the more information here, you'll see that it gives you some different resources. Some of them are talking about XOR. And the thing about XOR is it's a two-way operation. So if we've got a message here, CryptoCat is the best, and then we've got an encrypted message, if we were to XOR those together, it should recover the key that was used in the encryption. And we can test that out. Let's go and get the XOR recipe in cybersecurity, and I'll change the key to UTF-8. I'll paste in CryptoCat is the best and see what we've got out here. It looks like the key. You can see that it's repeating itself, so we'll try and work out where it ends. I think it is just this part. And now if I change this around and do that is the key, you'll see it's produced CryptoCat is the best. And just to visualize that, just in case you haven't done these basic XOR operations before, let's say we've got some plain text and we'll just make up a binary value. There we go, just make that up. And then we've got a key as well. We can also make this up. And to find the ciphertext, or to generate the ciphertext from this, then we would just XOR these together. So an exclusive OR will be a 1 if we have a 1 and a 0, or a 0 and a 1. But if we have two 1s or two 0s, it'll be a 0. Simple as that. So in this case, we've got a 1 and a 0, so it's a 1. We've got two 1s, that's a 0. 1 and a 0 is a 1. And we just keep going in this fashion until we get our ciphertext. Now, we've got three pieces of information, and with any two pieces of this, we can recover the third. So if we've got the key and the ciphertext, we can XOR these together and recover the plain text. Let's do that now. 1, 1. 1, 0, 1, 0, 1, 0. If we double click that, we'll see that we've actually got back to our plain text, but that could have been the other way around. We could have had the plain text and the ciphertext, and then if we XOR those together, we would have got the key. So let's do 0, 1, 0, 1, 1, 1, 0, 1. There we go, we have recovered the key. Alright, that's it. Anyway, that's how we could solve the first part. Let us go back here and just have a look at the source as well. I didn't actually check the help menu there, but it just gives us a little bit of about saying that we're going to look at three different weaknesses. First is using encoding instead of encryption, which we just saw. The second is using algorithms with known weaknesses. And the third is padding oracle attacks. And yeah, if we check the source for the low level, we will see that we have that key that we just saw. And it essentially will take our clear text, or plain text. It'll take the key, and then it's going to loop through the clear text, and it's going to loop through the key, and it's going to XOR each one of those characters together, and then produce the encrypted value. And it's as simple as that. Let's go now and change the difficulty to medium. Okay, and this time it says you've managed to get hold of 3 session tokens for an application you think is using poor cryptography to protect its secrets. So we've got one for Sutty, who is an admin, but the session has expired. We've got one for Sweep, who is a user, also expired. And we have one for Sue, which is a user, and the session is valid. This is the format of the token based on the documentation. So we have these tokens, and they contain a user, an expiry, a level, and a bio. And we're also told that it uses AES 12A ECB throughout the application. This is electronic codebook mode. And it's a block cipher, so our plaintext will be broken up into fixed size blocks of 128 bits or 32 characters. And whenever the encryption occurs, it will apply the key against each one of those blocks. And there is an issue with that, which we'll see quite shortly. Let me just first take a copy of these to our Sublime text editor. So we'll grab each one of the users. I want to break these down into those fixed size chunks so that we can visualize them a little bit better. And to do that, we'll say we want to get all characters between 0 and 9 and A and F, so that's all hex characters. We want to grab them in 32 character chunks, and we also want to capture them so that we can replace them here. So now what I'm going to do is say each one of those 32 character chunks, I want you to just replace it with itself, but add a new line between them as well. And if we do replace all, that will break that up nicely. So what was our goal? Our goal was to manipulate the session token to log in a sweep with admin privileges. So we've got the sweep user. The problem is the session's expired and they weren't an admin either. But we know what the format of these is. So we know that this is the user, this is the expiry, this is the level, and then anything after is the bio. And we want the expiry to be correct. So this one is the session valid here, which is the second row. So if I take the second row here and replace it here, and actually while we're here, notice that these two have the same value here. It's because they had the same expiry. And that's the issue with this encryption type, is that we're able to determine, so let's say this was a password in here and these two users were using the same password. It would be possible to see that the other user is using the same password because there is repetition in the ciphertext. Anyway, all right, let's change that. So we change the expiry. We also want to change the level. So we want the admin from the first one, and that's the third row. So we'll grab that. We'll change it to this one here, third row, and let's get rid of this. We want to join this all back together. I don't know what the easiest way is. I'm just going to get rid of our old users, and I'm going to just replace the new line with nothing. We replace it, we take a copy of that, and let's try and submit the token. And it comes back and said, we have been welcomed as the administrator sweep. So we've sent a valid token now, which was the user we wanted, using the admin privileges from this user and the valid session from this user. And if we go down here and open up the source, I don't think there's too much to look at here. We have the decrypt function, which is using OpenSSL's decrypt. It takes in the ciphertext, the ECB128 mode that we saw, and the key, the type of padding, and it'll perform the decryption. We can also see the key in here as well. And that's it. Let us go to the final level, which we can complete, which is the high level. And we'll go back here. It says, you've managed to steal the following token from the user of a prognostic application. And we've got a token and an IV, which look to be base64 encoded. You can use the form below to provide the token to access the system. You've got two challenges. First, decrypt the token to find out the secret it contains, and then create a new token to access the system as other users so you can make yourself administrator. All right, so it's got the token. It says, welcome back, Bungle user. So that is the token that we currently have here. And I'm going to go straight down to the help section. I'll be honest that I'm not particularly good at cryptography. I don't particularly like cryptography, and I'm looking forward to getting on to the next section of API hacking. So let's just try and get through this. You'll see that even here, the author of DVWA has said that this is vulnerable to a padding oracle attacks, which is using CBC mode now instead of ECB mode, so cipher blockchaining instead of electronic codebook. And that basically means that each plaintext block will be XORed with the previous ciphertext block before it's encrypted with the key. So that will prevent that repetition that we saw in the ciphertext. However, it will be vulnerable to this padding oracle attack. And as you can see, they didn't really put too much info here. There is just a link to this page, which I'm also going to open up. And there is also a script that we can run as well. If you click this, it will just download that script. So what you want to do is go to the actual directory on your system. You can see the path at the bottom, and that will make sure that all of the relevant files that it needs to include will be there as well. So we'll take a look at that shortly. Let's just go over to this article. And this is really good. I'm not going to obviously read through the whole thing. There's also a video, I guess, by the same author, which is like an hour long, and they talk very fast, I think even faster than I talk, but it is good content. So if you're still confused, I recommend to check that out. So what are the core concepts? We've got the block cipher, and we've already seen this in the previous example. We have fixed size blocks, and then some key and encryption algorithm will be used on each one of those blocks. We've also got a padding scheme, so because it's fixed size blocks, we need some way of padding out messages to make sure that they fit those block sizes. And this is a type of padding which is quite common, which basically says we'll append n bytes of value n. So if the padding is 8, it will append 8 bytes which are the value of 8. If the padding is 7, it will append 7 bytes where each one of those bytes is a 7. And that's that, yeah. So the block cipher mode is what we just discussed. So it will use each output of the ciphertext on the next block of plaintext before it uses the key to prevent that repetition throughout. And the initialization vector. So this is just what should be like a random block at the start because we don't have any ciphertext to XOR the first block with. So we will XOR it with the IV. And the padding oracle. So this is something which, given a ciphertext, will tell us whether its decrypted plaintext has valid padding or not. And it gives some examples here to explain this in a little bit more detail, but essentially the system will respond differently to valid versus invalid padding. So maybe you have a API which returns decryption error for bad padding, but it will return deserialization error for valid padding. So that's information leak that we can use to determine whether the padding is valid. And even without those error messages, we could have some timing differences which would make it possible, similar to what you see with like blind SQL injection, where you can have error-based or time-based. Okay, and here's an example, a diagram just showing what I was explaining there. So we have an initialization vector at the start, and it's going to XOR that with the first plaintext block before it does the encryption with the key. And then whenever it gets onto the next block, it's going to use the output of that. So the first ciphertext block will be XOR'd with the second plaintext block, and then it will be not just XOR'd with the key, but it will go through the AES encryption. And that shows how that works. Let us go down to the attack, the single block case. So they've simplified this to a single block just for the example. And yeah, let me just read through this. It says, say we pass an arbitrary block of ciphertext to our padding oracle. We can then set the IV to whatever we want. So we'll zero the whole IV to begin with. And we will start with the plaintext. We'll start with a block at the end. So you can see here we're going to flip a bit in the IV. So we'll start with the 16th element or the 15th element, which is starting at 0. And we will keep changing that value. We'll brute force through all possible values until we get back some valid padding. So we'll loop through 255 possible values. If we get back an error saying that failed to deserialize, then we know that the padding wasn't valid. But if we get back a message saying that the decryption failed, then we know that the padding was valid. And it gives an example here. So in this example, they found that they looped through all the possible values for the final value of the IV. And whenever they got to 2E, they got back the message indicating that the padding was correct. And that's because it had XOR'd the 2E with the 2F at the end of this decryption process. And the output was 0, 1, which is 1 byte of padding. And essentially, once you've identified that, you can then work on the next byte, and it'll go through and it'll be changing this to a 2 until you've got those 2 bytes of padding working. And then it'll change it to a 3, and you basically need to keep going through the entire thing. One thing to mention also is that it is creating a zeroing IV. So I can't remember. Yeah, zeroing IV. Okay, so why 0? 2 reasons. One is useful now, which will come later. And the reason is 0 gives us options. If we want to set a plaintext byte to any byte other than 0, we can just XOR that value into the zeroing IV. So in other words, the zeroing IV will give us a way of manipulating the plaintext however we like. So how do we build this? Well, we found that the value at the end, we found how to achieve the 0, 1 padding at the end. So we'll take the corresponding byte of the IV and XOR it with a 1, and that will set it to a 0. And we basically keep doing this for each one of the bytes until we get this zeroing array. And it will make it easier at the end of the process to then modify the IV in a way that we can influence what the plaintext equals, because we want to be able to change the user or the privileges once we've actually decrypted this. Okay, probably a terrible explanation. I recommend just reading through this and maybe going through the hour-long video because I'm not the best person to explain this, but we've got a sample implementation, and we also had the example that they gave in the DVWA lab, so let's go and take a look at that script also. Actually, while we're doing that, or just before we do that, let me also take this IV and let's go and change this from base 64, or let's get rid of the XOR. Where is it? It's not CryptoCat is the best. Why is it showing that? Okay, that's what it is. All right, so the IV is currently just 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. And we could actually use Hackverter in Burp. Let me send this to the repeater. All right, so this is the post request it's making to check the token. I'll send that to the repeater, and here's our token here. What I'm going to do is get rid of the IV, and I'm going to insert the Hackverter. We will encode it to base 64, and then I'm just going to put in, oh, not that, I want to put in the base 64 decoded value. It's just going to be a way that we can easily manipulate this. We could also do this with Intruder as well. So now if I do send, so that works. So it's basically base 64 encoding this before it sends it across. And it means I can go through and start changing some of these values. Like if I change that to a 9, you'll see that it comes back saying that the decryption failed. So we could change it to a 7, a 6, a 5. We can keep going through and seeing how that responds. I'm not going to manually brute force that. Let's go and have a look at the script. And you can see that this is just a script that they gave. I just had a look at the options that were in it, and we provide an IV, we provide the token, we provide the URL, and then I'm also sending the output to just an output file because I added some more debugging statements into it and it creates quite a lot of output. So let's just run this first of all, and then we'll open it up and see how it looks. All right, so it ran, and we're going to open up temp output. All right, so starting with the final byte, you can see that it set the IV to all zeros, and then it's going through each of the final bytes and just incrementing one by one. It goes through until it gets to this one, 31, and it says, got a hit for 49 at offset 15. So it's kind of annoying that it's given here in hex and then here in decimal, and nowhere does it give us the ASCII value. We could do it in CyberChef, or we can go to something like ASCII to hex, and let's just say that the value here was 31, so it came out with a 1. So yeah, because we're looking for it to equal a 1 with a padding at the end. And let us verify that. Let's go to Burp and let's change that final value to a 1. We click send and it says no user specified. So if we change it to a 2, we will see that it failed. If we change it to a 0, we will also see that it failed. But yeah, if we change it to a 1, we'll see that it doesn't fail. And we can basically keep going in this way. So you can see that it's found that, and then it also does the XOR in order, because we want to make this zeroing array, right? So this is the start of our zeroing array. And then you can see now that it changed that to from a 30 to a 32. That's because we're now looking for 2 bytes of padding. You'll see that the next time it's going to do 33, etc. But anyway, it gets down to here. We get the 32 and the 3D. And again, this gets added here. We do the XOR. It's a little bit confusing. We do the XOR with the number of bytes of padding, and that's what gets added to our zeroing array. And you can go and test this out manually. So you can go and put these 3 values into the IV here and allow it to encode. Yeah, you can work through this. Essentially, it's looping through until it builds up this whole zeroing array. And then if we get down to the output at the bottom, somehow, yeah, if we get down to the output at the bottom, we end up with, so this was the real IV that we started with, and then we have the derived IV and the zeroing array, and through this we're able to decrypt the original string. So it actually decrypted it to, it decrypted it and then it modified it so that we now have the user of Jeffrey and the admin, so it gave us a new token at the end. So if I take a copy of this and go back to, actually let's just go back to here, and we'll paste it in here, and yeah, there we go. We get the Jeffrey admin. Let's take a look at the value of this. So it was 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. Now it is it the same? I don't actually see any difference there at all. Maybe I didn't copy it right. Okay, let me take the original. Too many windows open, and oh yeah, now it wants to give us something different, does it? Yeah, this S has changed to a G, so I don't know why it's now suddenly changed this to a colon. But anyway, let's go back to Burp, and if I now go, and I'll just take a copy of this. This is the one that's working. So we can see that the bit that had to be flipped in order to make this work. And now if I just go and try and play around with that, you see we've got Jeffrey at the moment. If I go and change this to, let's change it to, what was it originally? It was an 8, right? Let's change it to a 9. Now we are user zippy. All right, let's change it to 8. We are bungle. We could change it to a 6. no user specified. Okay. And we can basically keep working our way up and see what values here will change to different users. All right, I'm aware that was probably a terrible explanation. I'd recommend just going through some of this in your own time. I remember Hack the Box also had a challenge on some of this stuff. I think it was called I Know Magic, which you could use a pad buster tool for. I did actually try to use that here as well. It's, I think, installed by default in Kali or Parrot, but I couldn't get it working. Maybe somebody else can. And let's just take a look then at the final thing. We can go and change the difficulty to impossible. And if we go back to cryptography, we'll see that now it's not possible for us to mess with the token anyway, but we can feel free to do so. If we take a look at the source, we will just see that this is... Oh, okay, well, I guess it's importing from another library, which I can't be bothered to go and manually open up. But let's just assume this one's secure, and it means that next time we can move on to the API hacking labs, which should be a little bit, hopefully easier, but also more enjoyable. Unless you really like crypto. Anyway, I hope you enjoyed this video. If you have any questions or comments, leave them down below. Thanks.